So today we are studying astrophysics and cosmology. Use the techniques and idea of physics to study the heaven is often referred to as astrophysics. Central to our present theoretical understanding of the universe is Einstein's general theory of relativity and the modern theory of gravitation. Many other aspects of physics are involved, from electromagnetism and thermodynamics to atomic and nuclear physics as well as elementary particles. General relativity serves also as the foundation for modern cosmology, which is the studying of the universe as a whole. Cosmology deals especially with the search of theoretical framework to understand the observed of universe's origin and its future. In cosmology, we ask questions like, had the universe only exist? Did it have a beginning of time? Is time going back to infinity? Or was there anything before when time began? According to the ancients, the stars, except for the few that seemed to move, were fixed on a sphere beyond the last planet. The universe was nearly self-contained, and we on Earth were its center. But in the last century following Galileo's first telescopic observation of the heaven in 1610, our view of the universe has changed dramatically. We no longer place ourselves at the center, and we view the universe as vastly larger. Because the distances involved are so great that we specify them in terms of time it takes light to travel the given distance. For example, one light second is 300 kilometers, one light year is 10 to the 13 kilometers. Why are we using these values instead of just kilometers? Because, for example, just in our solar system, the distance to travel from Sun to Earth is roughly about 150 million kilometers. And this is only about 8.3 light minute. That's why if we want to get over our solar system, expanding to the galaxies and travel to the other place of the universe, we have to use light years instead of the small scale of the kilometers. On a clear moonless night, thousands of stars of varying degrees of brightness can be seen, as well as the long cloudy stripe known as the Milky Way. Galileo first observed with his telescope that the Milky Way is comprised of countless individual stars. About 1750, Thomas Wright suggests that the Milky Way was a flat disk of stars extending to a great distance in the plane, which we call the galaxy. Is a Greek word for the Milky Way. Our galaxy has a diameter of almost 100,000 light-years and a thickness of roughly 2,000 light-years. It has a booming central nucleus and a spiral arm. Our Sun, which is seen to be just another star, is located about halfway from the galactic center to the edge, some 26,000 light-years from the center. Our galaxy contains roughly 100 billion stars. The Sun orbits the galactic center approximately once every 250 million years or so its speed is around 200 km per second, relative to the center of the galaxies. The total mass of all stars in our galaxy is estimated to be about 2 times 10 to the 41 kg, which is ordinary matters. In addition, there is strong evidence that our galaxy is surrounded by an invisible halo of dark matters. So this is evidence. We can use Newton's second law, F equals ma, and in this case F is g times the mass of the galaxies times the mass of the Sun over the radius square equals the mass of the Sun times the velocity square over the radius. And so by crossing out the same mass of the Sun, we have the mass of the galaxies equal the radius times the velocity square over the constant g. So it would be about 26,000 light years times 10 to the 16 meters over light years times 2 times 10 to the 15 meter per second square over 0.67 times 10 to the negative 11 newtons times meter square over kilogram square, and is about 2 times 10 to the 41 kilogram. In terms of a number of stars, if they are like our suns, the mass is about 2 times 10 to the 30 kilogram. That would be about 2 times 10 to the 41 over 2 times 10 to the 30, so it will be about 10 to the 11 or 100 billion stars. An important astronomical discovery made around 1900 was that for the most stars, the color is related to absolute luminosity and therefore to the mass. A useful way to represent this relation is by so-called Hertzsprung and Burchell diagram. So on the HR diagram, the horizontal axis shows the temperature T, whereas the vertical shows the luminosity. Each star is represented by a point on the diagram. Most stars form along a diagonal plane termed the main sequence. Starting at the lower right, we find the coolest star in reddish color. They are the least luminous and therefore of low mass. Further up toward the left, we find hotter and more luminous stars that are whitish, like our Sun. Still further up, we find still more massive and more luminous stars, bluish in color. Stars that form on a diagonal plane are called main sequence stars. There are also stars that form outside the main sequence. Above to the right, we find extreme large stars with high luminosities but with low reddish color temperature. These are called red giants. At the lower left, there are a few stars of low luminosity but with high temperature. These are the white dwarf. So okay, Adam, what are the color of the star and what do they stand for?
Okay, so there are like four different colors of stars, and they each stand for like a specific temperature range. Red is around about 3,000 degrees Celsius, yellow around 6,000, bluish white around 10,000, and blue around 40,000 degrees Celsius. And the sun, for example, is yellow, and it is around 6,000 degrees.
By the way, we talk about the star. I've heard
Mm-hmm.
rumors that like our sun is not gonna be here to infinity. They're gonna be here for like another few years or something.
Yeah, their sun will definitely not be here till infinity, but actually, the sun is going to be increasing in size in the next couple years. In the past 4.5 billion years, the sun has increased by 30% in its size, and it will continue to expand as it runs out of hydrogen. In around like 5 billion years, the sun will actually turn into a white dwarf, and as it's expanding, it's going to increase in its heat and actually destroy pretty much everything on the Earth.
Well,
Yeah.
I don't think that's a big problem because I don't think we're gonna be here for another billion years though. I think we're gonna run out
Probably
of
not.
natural resource in a few thousand years. So thank you for interviewing me today.
No problem. Thank you for interviewing me.